Imagine a universe not built from tiny balls, but from a swirling sea of energy. This energy, ever-changing and vibrant, gives rise to the very particles we think we know. This, my friends, is the mind-bending world of quantum field theory, and this is just the beginning of our exploration. Welcome to the first episode of this series on the concepts of quantum field theory, where we target to understand, explore, and go deep to the fundamentals of this elegant theory, thereby unraveling the most important, complicated, but yet an emerging concept of science. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to the first episode on building the basic concepts of quantum field theory. Before we go ahead and go deep into the complicated mathematics and concepts of quantum field theory, it is essential for all of us to know how a system evolves or how the entire quantum field theory evolved. And this is what is called the evolution of quantum field theory. As you see here right on the screen, that when human beings started to evolve from ape men, we started to grow and evolve to the modern human being. As you can see that the brain structure also evolved from the Neolithic, Paleolithic ages to the modern humans. Human beings started to mature, and as you can see that we have got evidences in the Mayan, Aztec, Harappan and other civilization that human beings started to worship the different forces of nature. As we call that necessity is the mother of invention, human beings and we started to develop hunting instruments in order to hunt wildlife so that we can eat and live and thereby grow and more evolve. Apart from that, as you can see that the entire automobile system evolved. So from 1886 to 1900s and then to 2024, how the automobiles and the structure evolved. Also, you will see that the entire living style of evolution from the hut to the further areas and then to the modern home. The evolution of dress, how it evolved, although it sounds funny, but this is also has been an evolution process. The eating style that we do today at the fine dine restaurants, etc., in different places also evolved because the eating style was not the same during our early ages. The entertainment, the smart television that we had today, if you look into the 1930s and 1970s, the televisions were quite huge, quite big in size. So the most important part, which is very significant in their entire process of evolution, is that things started to grow smaller, things started to become more portable, and things started to take one particular unit which has many features. As you see, big phones have now, the landline phones have now been reduced to smartphones. And even one smartphone has got a lot of features. One television has got a lot of features. One car has got a lot of features. It is not only for moving around, but it is for dining, eating, drinking, and so. So the basic idea, what I'm trying to make a point, is that evolution process also involves what is called reducing the sizes of instruments and making it portable. So as we started taming the nature and things started to take a much portable size, physics, mathematics and science also tried to get into one particular system which will be much smaller, much coin size and much portable. In this journey, we identified the fundamental forces of nature as first was the gravity, then it was the strong force which holds the proton and the neutron in a nucleus, the weak force which is responsible for decay, and the electromagnetism which was earlier considered to be different forces as electricity and magnetism. So as you see that now, as I was telling that everything we try to put it in a much portable, smaller fashion, so we also try to do with physics. So we try to unify gravity with strong force and weak force along with electromagnetism into something unique, something which is called one single grand unified theory or a theory of everything, which we are still striving to achieve. So the basic idea and the concept remains the same, that we are all trying to get things into one single theory. So just like smartphones, just like smart televisions, we get into one theory which is compact, concise and portable. And from here we can say that quantum field theory is a type of a theory of everything which aims to achieve a type of unification which encompasses multiple branches of science and mathematics and physics. What are those branches that we will take into account in the next part of the video? So till now we understand that the need for a quantum field theory is basically to unify all the forces of nature and take all the mathematics, all the science and all the complications in a much more portable and an easier manner. But the question still lies that what actually is quantum field theory, although it is considered one of the candidate of the theory of everything. Coming up into the next part of the video, what is quantum field theory? So in theoretical physics, we call quantum field theory is a theoretical framework which actually unites classical field theory, special relativity and quantum mechanics. Now why do we call it a theoretical framework, not a scientific framework? There are reasons, because all the predictions and formulations of QFT has not yet been experimentally approved or experimentally verified. So we have one end the classical field theory, which is of Newton's and Maxwell's equations. We are trying to combine with special theory of relativity and quantum mechanics and get into something which is called a quantum field theory. Now this classical field theory is something we can take up in another video, or you can attend to my live classes which I have already started, which is called the basic concepts of quantum field theory. So it actually shows how one or more fields they interact with matter without considering the effects of quantization. Obviously if you take the concept of quantization, it is not classical, it becomes quantum. But most important is that this field is spread out, and over the entire spread of space and time we have each and every point to be denoted. So from here what we can find is that field theory or classical field theory is not only related to QFT, but it is also related to Newtonian gravitation, Maxwell's equation, Faraday's law of electric lines. So all these actually are field theories. These are classical field theories, however we are much more interested in quantum field theory. So you see from here what we get is that we get a unified description, and that is the need that of a quantum field theory, that it provides a single portable coincide framework. Also it is responsible definitely for technological advancement, because these insights have helped into development of lot of technologies, lot of advancement in terms of communication, security, cyber security, and a lot into the current stage. Also what is important is interdisciplinary application. That means we can actually use QFT in condensed matter physics, superconductivity, and what is called a quantum Hall effect. So at this point of time we understand the need of a quantum field theory in getting all the four forces of nature into something, a single coincide portable theory. And what is quantum field theory? It is discarding general theory of relativity, and it is just taking 1, classical physics, 2, special theory of relativity, and 3, what is called the quantum physics. Now that we know, there must have been a kind of a limitation. There must be a limitation into the earlier theories of classical or whatsoever, and that is why we need a new theory. Otherwise, why will we go and get a new theory with all those complications? So here we come to the next part of our video, that why do we need quantum field theory, or you can even tell that what were the limitations of earlier theories that led to the appearance of quantum field theory, coming up to the next part of our video. So the earliest successful classical field theory is one that emerged from Newton's law of universal gravitation, which was published in 1687 by his treatise Philosophiae Naturalis Principia Mathematica. The force of gravity as described by Newton is an action at a distance, and its effects on faraway objects are instantaneous. Now fields began to take on an existence of their own with the development of electromagnetism in the 19th century, and Michael Faraday was the first person to coin the English term field in around 1845, and he introduced fields as property of space. The theory of classical electromagnetism was completed in 1864 with the Maxwell's equation, which described the relationship between electric field, the magnetic field, the electric current, and the electric charge. Now, in spite of the enormous success of classical electromagnetism, it was unable to account for the discrete lines in atomic spectra, nor the distribution of black body radiation. So here you can see Max Planck's study of black body radiation marked the beginning of the quantum era. He treated atoms which absorb and emit electromagnetic radiation as tiny oscillators. And then came the big idea. Albert Einstein proposed in 1905 an explanation of the photoelectric effect, that light is composed of individual packets of energy which are now called photons. As we turn the pages of history, we come to 1913, where Niels Bohr introduced the Bohr model of atomic structure, wherein electrons within atoms can only take a series of discrete rather than continuous energies, and the concept of quantization emerged. In 1924, Lew de Broglie, a student of history, proposed the hypothesis of a wave-particle duality, that microscopic particles exhibit both wave-like particle-like properties under different circumstances. Now, as we unite all those scattered ideas, a coherent discipline which is called quantum mechanics emerges between 1925 and 1926 with Max Planck, Lew de Broglie, Werner Heisenberg, Max Born, Erwin Schrödinger, Paul Dirac, and Wolfgang Pauli, which we call now as quantum mechanics. So this was the journey from Newtonian mechanics to quantum mechanics, and how, remember, we are not considering general theory of relativity because it is out of scope of the current scope of QFT. So we see that this is how things emerges and we come to the quantum era. Now here comes the most important part. Now we know that the entire realm of Newtonian physics, whatever it is, has been expanded, generalized with the speed of light, time dilation, length contraction into what is called the special theory of relativity, published in 1905, and which we call it as Annus Mirabilis, or the great time, the time when actually Einstein published it. Now, Newtonian physics we are not considering, because all the aspects of Newtonian physics has been emerged into special relativity, with all those what we call the 4 vector, 4 momentum, 4 force, 4 acceleration. And on the other hand, we have the new era, which is the quantum physics, where people like Max Planck and Erwin Schrödinger are dominating the world. Now the question arises that now we have two theories, special relativity and quantum physics. How can we unite special relativity with quantum physics? And this is exactly which is done by quantum field theory. Although there are many propounders of quantum field theory, however, I have mentioned the name of Dirac for a specific reason, which will come clear. So now we have got special relativity and quantum physics, both of them emerging into one single theory, which is called the we call the quantum field theory. So you see that how things slowly are getting coincised and shortened and more portable. One theory is already of Newtonian physics. Now we are trying to get special relativity and quantum physics into one single theory, which is called the quantum field theory. So as we turn the next pages, we see that in general, when quantum physics was first founded, it was basically a non-relativistic nature. That means relativity definitely was not considered into the area of quantum physics. And if you go to my live lectures video, you will see that in one of the videos I have actually described that Schrödinger equation was not relativistic, but it was very classical in nature. And from Schrödinger equation was basically I would say an extension of the Newton's laws of motion. You can go to my live section and we'll see why Schrödinger equation is considered to be classical, and I have shown a mathematical deduction of that. Anyway, so what we understand that because it was non-relativistic in nature, and there was a limitation in terms of incorporating those equations to special relativity and high-speed particles or high-energy physics. So during that time, there were two equations which was founded. One was the Dirac equation by Paul Adrian Maurice Dirac, a British physicist and a scientist, and another was Klein Gordon equation, which was found by Oscar Klein and Walter Gordon. Now these two equations were basically an attempt to put the relativistic part of special relativity into quantum mechanics. This was the early attempt, but there was a problem. Now what was that problem? Let us see. Now so you see that Klein Gordon equation actually describes spinless particles which can be called pions. And Dirac equation actually follows the spin half particles which are fermions, which follow the Bose-Einstein statistics. Fermions, the Fermi-Dirac statistics, I'm so sorry. So the Klein Gordon equation as well as the Dirac equation was trying to unite quantum physics and special relativity into something. We don't know what is that something. Remember, this something is actually the quantum field theory. But the problem that emerged is that, say for example, if I take the Klein Gordon equation, it allowed solutions of both positive and negative energies. So both equations allowed for solutions with negative energy values. And if you imagine an electron with negative energy value, it would not behave like the familiar electron, isn't it? So the sea of negative energy was a major hurdle. And it predicted a very unstable universe filled with these negative energy particles which contradict actually the observations. So what we see is that this was the negative energy part. So in quantum mechanics, a negative energy actually contradicts the what we call is the causality. And so you can imagine an electron which is moving in the opposite direction. So the Klein Gordon equation described basically a spinless relativistic particle. It successfully predicted some properties of particles, but the negative energy solution made the concept very unstable. So as you see, physics energy is fundamental and it should be either positive or zero. So in classical mechanics, we know that particles have energy associated with their mass and motion. So a negative energy means it would not correspond to any particle. So the Dirac equation, which was similar to the Klein Gordon equation, addressed the spin issue by describing the relativistic particle with spin. It yielded solutions which is consistent with electrons and positrons, that is anti-electrons. However, the negative energy solution became again a causality issue, just like the Klein Gordon equation. And for that, he actually proposed something which is called a Dirac sea. So Dirac sea is actually fascinating, but ultimately a superseded concept in physics that actually arose from Dirac equation. So it is a theoretical model for the electron vacuum, and the Dirac equation aimed at describing the relativistic electrons which predicted an unexpected result, and it allowed for I would say negative energy states for electron. So the problem was that this: according to physics principle, particles tends to minimize their energy. So shouldn't electrons be constantly dropping down and down and down to those negative energy states? So he proposed that the vacuum is actually a sea of, remember this is again theoretical, infinitely many electrons all occupying these negative energy states. Since all the negative energy states are filled, electrons would not normally fall into them. But the twist is that a vacancy or a hole in this Dirac sea would behave like a particle with positive energy and opposite charge of an electron. This hole remarkably lined up with the properties of the positron, the anti-particle of the electron, which was not discovered during that time. So while the concept of a literal sea of negative energy electron is not how physicists view the vacuum today, but the core idea was basically a stepping stone. So you see, it was difficult to reconcile with the idea of finite vacuum energy, and it was difficult to reconcile with the idea of finite vacuum energy. So, but the stepping stone was that it predicted the existence of a positron, later confirmed in 1932, and it offered a way to understand how particles and anti-particles could coexist. So the Dirac sea itself had limitations. It was difficult to reconcile with the idea of vacuum energy, and it actually didn't handle what is called the creation and annihilation in a very good mathematical or a good manner. So this was actually the formation of the Klein Gordon and the Dirac equation and the problem, and every problem would have a solution, but those problems had consequences, and the consequence was finding the anti-particle concept of positron around 1932. So what was the solution? Before that, we need to look into our final summary. So the Dirac equation and the Klein Gordon equation both actually showed the negative energy solution, which created a problem that particles could theoretically transit to lower, which I was stating, and it leads to instability. Now all these problems actually were the limitations which led to the formulation of quantum field theory, where these problems were eliminated and we get a much brighter sunshine and a sophisticated understanding of particles and antiparticles. Now what are those particles and antiparticles that we were talking about? Let us look into the next part of the video, where we will understand the particle and antiparticle creation and annihilation. Now remember, this particle and antiparticle creation and annihilation was also there, but quantum physics did not have that elegant mathematical tool to describe them. So here you see that classically, if we talk of these particles which are, have their energy and momentum and etc. So they are well-defined numbers. Now cosmic rays are high energy particles originating from outer space that constantly bombards the Earth. Now when these cosmic rays collide with the particles or with the nuclei of Earth's atmosphere, they create a lot of secondary particles through high energy interactions. For example, a gamma, an electron and positron, etc. So there has been several key discoveries which are related to rays, which has highlighted the particle creation. So this is, we call that the cascade of particles is an example that particle creation was already happening. And as you see, new particles are emerging from the interaction between the initial cosmic ray and the atmospheric nucleus. Now the question that rises is that these observations challenged the fixed particle framework or the traditional quantum physics or whatsoever was there, and it was unable to give a elegant theoretical framework. So the creation and annihilation of particle from the cosmic rays first was a problem. Now Carl David Anderson actually already has discovered the positrons, the antiparticle of electron, while studying cosmic rays in the cloud chamber. Now he also observed that tracks that could only be explained by the presence of a particle with the same mass of an electron but which has got a positive charge, so E+. Now this discovery demonstrated that particles could be created, although not only this one, we will look into the other ways of particle creation, implying that particle antiparticles could be produced. But the question is that, do we have a system? I should say that, was there a system that was mathematically consistent to describe what is called a particle creation? The answer was a no. And this no actually helped us to form what is called a quantum field theory. So these, I would say, bottlenecks, these problems will actually make you understand that why quantum field theory at all emerged. So the first thing was the particle accelerator. So these experiments provided clear evidence that particles could be created from energy consistent with Einstein's equal to mc squared. The second was particle collisions in the middle of the 20th century, because numerous new particles were found. So the proliferation of discovered particles indicated that high energy collisions could create a variety of particle antiparticles, necessitating a theoretical approach that could handle varying particle numbers. And the Large Hadron Collider. These annihilation events where the particles disappear and their mass is converted into energy, which is generally gamma rays, reinforce the concept of particle-antiparticle pairs and the need for a theory that describes both creation and annihilation. So from here we find a conclusion that these observations actually supports the creation and annihilation of particles, and we find now an elegant super theory that explains these phenomena by viewing particles as excitations of underlying quantum fields. Remember, particles are no longer particles, these are excitations. And the creation of a particle corresponds to an excitation appearing in the field, when annihilation corresponds to the excitation disappearing. Now when we talk that, as I told you, that these are not particles but excitation, we come to the next part. What are those excitations and where does those excitation really happen? And we come to the final part and the most important part of our video, which is called fields and particles. Now, as far as the classical theory of quantum mechanics is concerned, generally we consider particles as the fundamental objects. Even if you go deep down and break the fundamental particles, these actually build up their masses and whatever we see around the universe. But these particles in quantum field theory got, I would say, extended into something which are called fields. Just to give you a clear idea, consider this part of a space and there are so many fields. So quantum field theory, what it did, it proposed that instead of small individual particles or billiard balls, all of space is permeated by a field. So just imagine a space. And these fields are non-localized entities that exist through space-time. I am not going to explore or tell you what is a non-localized entities, because those who know quantum mechanics, you already know that. So this is it is permeated, it is spread out, it is a space which contains the fields. So we know that particles earlier, that they were the building blocks of the universe. They exist independently and two particles are exerting force on one on another. This was the classical theory. Now we find that fields are the fundamental entities, not the particles. And this is something which looks like this. And it permeates the entire space-time. Space and time or space-time. Don't think that again it is a space-time continuum, because we have discarded general relativity. So each type of particles is associated with a specific quantum field. For example, there is the electron field, there is a positron field, each and a Higgs field. So you can imagine some kind of an area like this, although it is a very rudimentary sketch. And these are the particles, and these particles, they excite. These particles are doing excitations. So particles are basically excitations of those fields, underlying fields, similar to the ripples on a pond. That means we can say that the pond which is spreading across an area is basically the field, and when you drop a pebble, the ripples are actually the excitations, and these are the particles. Now we are saying that fields are more fundamental, right, than the particles. Though the question is that why fields are fundamental. Let us look into this part of the video. So we have actually noted this kind of an area, and we have seen that these are the particles which have got the excitations. So in quantum field theory, we say that particles can pop in and out of the existence due to the fluctuations of the field. And the good part is that this phenomena does not contradict, and the conservation of laws and the symmetry, most importantly, are quite well maintained. So we get a particle and an antiparticle, they create and they destroy. So they are actually popping up, they are creating and they are destroying, but underlying there is a field which is responsible for the creation. And that is why we call fields are more fundamental. Also, most importantly, you will see that if we consider our state, which is a perfect vacuum, so even in quantum field theory, we don't consider to be an empty space, a perfect vacuum, because that also has a non-zero energy due to these fluctuations. We will look into this more into the next coming episodes. And this is crucial because particle and antiparticle creation and the Casimir effect actually helps in that. So that is why, again, reason 2, that fields are more fundamental, because vacuum is no more a vacuum. It has a non-zero energy due to these fluctuations. And most importantly, the field theory goes very well with special theory of relativity. As I will see that the special theory of relativity, when it is merged with quantum field theory, the symmetries are quite well maintained. So what happens from the physics when we move into the mathematics part, what we see is that the fields are now being taken as the particles into quantum operators. And the entire field dynamics is now being guided by what is called the Lagrangian as well as the Hamiltonian. I've just shown the Lagrangian here. And this, when we, from the Lagrangian, we can derive the equations of motion that govern the field. And these derivations are actually the partial derivatives, which ultimately give rise to the particles. And this interaction between fields are visualized by what we call is the famous Feynman diagrams, which are pictorial representation of the mathematical calculations, how particles come in, they join together, they dance, and they create antiparticles, they destroy, and again they create. So this is what I wanted to tell you into this part of the video, but we are not done. We have just started, remember, the first part of the episode where we are dealing with the fields and particles. But you see that I have talked about quantum operator, I have talked about Lagrangian, which I have not explained. And this is which is going to come up into the next part of the video. We are going to take a quick recap, and then we will deal more into how the fields dominate of the particles and how the Lagrangian and Hamiltonian formalism actually helps us in a better understanding. This we will deal in the next part of the video. I'm immensely thankful for those who have watched this video. If you have liked, please don't forget to hit on the subscribe button of my channel Phys for Students and click on the bell icon to get all the notifications. You can also write to this email ID where I always reply to my emails, and you can subscribe to my other channel, General Relativity Explained. You can also follow me on my Facebook, LinkedIn, Instagram and Twitter account. So that's all for today's video. I will wait for your comments, but coming up very soon is part 2 on the basic concepts of quantum field theory, where we will be actually describing more on fields and particles and then take the mathematics head on. Physics for Students will continue producing more such interesting videos, and I need your support to provide, to reach out, to share, to like, to subscribe, and to put up your comments. That's all for today's video, and may the good Lord be with you.